The interdisciplinary field of materials science, also commonly known as materials science and engineering, involves the discovery and design of new materials, with an emphasis on solids. The intellectual origins of materials science stem from the Enlightenment, when researchers began to use analytical thinking from chemistry, physics, and engineering to understand ancient, phenomenological observations in metallurgy and mineralogy. Materials science still incorporates elements of physics, chemistry, and engineering. As such, the field was long thought of as a subfield of these related fields. In recent years, materials science has become more widely recognized as a specific and distinct field of science and engineering. Many of the most pressing scientific problems humans currently face are due to the limitations of the materials that are available and, as a result, breakthroughs in materials science are likely to have a significant impact on the future of technology. Materials scientists emphasize understanding how the history of a material influences its structure, and thus the material's properties and performance. The understanding of processing, structure, properties relationships is called the materials paradigm. This paradigm is used to advance understanding in a variety of research areas, including nanotechnology, biomaterials, and metallurgy. Materials science is also an important part of forensic engineering and failure analysis, investigating materials, products, structures or components which fail or which do not operate or function as intended, causing personal injury or damage to property. Such investigations are key to understanding, for example, the causes of various aviation accidents. History. The material of choice of a given era is often a defining point. Phrases such as Stone Age, Bronze Age, Iron Age, and Steel Age are great examples. Originally deriving from the manufacture of ceramics and its putative derivative metallurgy, materials science is one of the oldest forms of engineering and applied science. Modern materials science evolved directly from metallurgy, which itself evolved from mining and ceramics and the use of fire. A major breakthrough in the understanding of materials occurred in the late 19th century, when the American scientist Josiah Willard Gibbs demonstrated that the thermodynamic properties related to atomic structure in various phases are related to the physical properties of a material. Important elements of modern materials science are a product of the space race. The understanding and engineering of the metallic alloys, and silica and carbon materials, used in the construction of space vehicles enabling the exploration of space. Materials science has driven, and been driven by, the development of revolutionary technologies such as plastics, semiconductors, and biomaterials. Before the 1960s, many materials science departments were named metallurgy departments, reflecting the 19th and early 20th century emphasis on metals. The growth of materials science in the United States was catalyzed in part by the Advanced Research Projects Agency, which funded a series of university-hosted laboratories in the early 1960s, to expand the national program of basic research and training in the materials sciences. The field has since broadened to include every class of materials, including ceramics, polymers, semiconductors, magnetic materials, medical implant materials, biological materials and nanomaterials. Fundamentals of materials science. A material is defined as a substance that is intended to be used for certain applications. There are a myriad of materials around us. They can be found in anything from buildings to spacecraft. Materials can generally be divided into two classes: crystalline and non-crystalline. The traditional examples of materials are metals, semiconductors, ceramics and polymers. New and advanced materials that are being developed include nanomaterials and biomaterials, etc. The basis of materials science involves studying the structure of materials, and relating them to the properties. Once a materials scientist knows about this structure-property correlation, she can then go on to study the relative performance of a material in a certain application. The major determinants of the structure of a material and thus of its properties are its constituent chemical elements and the way in which it has been processed into its final form. These characteristics, taken together and related through the laws of thermodynamics and kinetics, govern a material's microstructure, and thus its properties. Structure. As mentioned above, structure is one of the most important components of the field of materials science. Materials science examines the structure of materials from the atomic scale, all the way up to the macro scale. Characterization is the way materials scientists examine the structure of a material. This involves techniques such as diffraction with X-rays, electrons, or neutrons, and various forms of spectroscopy and chemical analysis such as Raman spectroscopy, energy dispersive spectroscopy, chromatography, thermal analysis, electron microscope analysis, etc. Structure is studied at various levels, as detailed below. Atomic structure. This deals with the atoms of the materials, and how they are arranged to give molecules, crystals, etc. Much of the electrical, magnetic, and chemical properties of materials arise from this level of structure. The length scales involved are in angstroms. The way in which the atoms and molecules are bonded and arranged is fundamental to studying the properties and behavior of any material. Nanostructure. Nanostructure deals with objects and structures that are in the 1 to 100 nanometers range. In many materials, atoms or molecules agglomerate together to form objects at the nanoscale. This leads to many interesting electrical, magnetic, optical and mechanical properties. In describing nanostructures, it is necessary to differentiate between the number of dimensions on the nanoscale. Nanotextured surfaces have one dimension on the nanoscale, i.e., only the thickness of the surface of an object is between 0.1 and 100 nanometers. Nanotubes have two dimensions on the nanoscale, i.e., the diameter of the tube is between 0.1 and 100 nanometers, its length could be much greater. Finally, spherical nanoparticles have three dimensions on the nanoscale, i.e., the particle is between 0.1 and 100 nanometers in each spatial dimension. The terms nanoparticles and ultrafine particles often are used synonymously, although UFP can reach into the micrometer range. The term nanostructure is often used when referring to magnetic technology. Nanoscale structure in biology is often called ultrastructure. Materials whose atoms, molecules form constituents in the nanoscale are called nanomaterials. Nanomaterials are subject of intense research in the materials science community due to the unique properties that they exhibit. Microstructure. Microstructure is defined as the structure of a prepared surface or thin foil of material as revealed by a microscope above 25 times magnification. It deals with objects from 100 nanometers to a few cm. The microstructure of a material can strongly influence physical properties such as strength, toughness, ductility, hardness, corrosion resistance, high-low temperature behavior, wear resistance, and so on. Most of the traditional materials are microstructured. The manufacture of a perfect crystal of a material is physically impossible. For example, a crystalline material will contain defects such as precipitates, grain boundaries, interstitial atoms, vacancies or substitutional atoms. The microstructure of materials reveals these defects, so that they can be studied. Macrostructure. Macrostructure is the appearance of a material in the scale millimeters to meters. It is the structure of the material as seen with the naked eye. Crystallography. Crystallography is the science that examines the arrangement of atoms in crystalline solids. Crystallography is a useful tool for material scientists. In single crystals, the effects of the crystalline arrangement of atoms is often easy to see macroscopically, because the natural shapes of crystals reflect the atomic structure. In addition, physical properties are often controlled by crystalline defects. The understanding of crystal structures is an important prerequisite for understanding crystallographic defects. Mostly, materials do not occur as a single crystal, but in polycrystalline form. Because of this, the powder diffraction method, which uses diffraction patterns of polycrystalline samples with a large number of crystals, plays an important role in structural determination. Most materials have a crystalline structure, but there are some important materials that do not exhibit regular crystal structure. Polymers display varying degrees of crystallinity, and many are completely non-crystalline. Glass, some ceramics, and many natural materials are amorphous, not possessing any long-range order in their atomic arrangements. The study of polymers combines elements of chemical and statistical thermodynamics to give thermodynamic, as well as mechanical, descriptions of physical properties. Bonding to obtain the full understanding of the material structure and how it relates to its properties. The materials scientist must study how the different atoms, ions and molecules are arranged and bonded to each other. This involves the study and use of quantum chemistry or quantum physics. Solid-state physics, solid-state chemistry and physical chemistry are also involved in the study of bonding and structure. Properties. Materials exhibit myriad properties, including the following: mechanical properties, chemical properties, electrical properties, thermal properties, optical properties, magnetic properties. The properties of a material determine its usability and hence its engineering application. Synthesis and processing. Synthesis and processing involves creation of a material with the desired nanostructure. From an engineering standpoint, a material cannot be used in industry if no economical manufacturing method for it has been developed. Thus, the processing of materials is very important to the field of materials science. Different materials require different processing, synthesis techniques. For example, the processing of metals has historically been very important and is studied under the branch of materials science known as physical metallurgy. Also, chemical and physical techniques are also used to synthesize other materials such as polymers, ceramics, thin films, etc. Currently, new techniques are being developed to synthesize nanomaterials such as graphene. Thermodynamics. Thermodynamics is concerned with heat and temperature and their relation to energy and work. It defines macroscopic variables, such as internal energy, entropy, and pressure, that partly describe a body of matter or radiation. It states that the behavior of those variables is subject to general constraints that are common to all materials, not the peculiar properties of particular materials. These general constraints are expressed in the four laws of thermodynamics. Thermodynamics describes the bulk behavior of the body, not the microscopic behaviors of the very large numbers of its microscopic constituents, such as molecules. The behavior of these microscopic particles is described by, and the laws of thermodynamics are derived from, statistical mechanics. The study of thermodynamics is fundamental to materials science. It forms the foundation to treat general phenomena in materials science and engineering, including chemical reactions, magnetism, polarizability, and elasticity. It also helps in the understanding of phase diagrams and phase equilibrium. Kinetics. Kinetics is the study of the rates at which systems that are out of equilibrium change under the influence of various forces. When applied to materials science, it deals with how a material changes with time due to application of a certain field. It details the rate of various processes evolving in materials, including shape, size, composition and structure. Diffusion is important in the study of kinetics as this is the most common mechanism by which materials undergo change. Kinetics is essential in processing of materials because, among other things, it details how the microstructure changes with application of heat. Materials in research. Materials science has received much attention from researchers. In most universities, many departments ranging from physics to chemistry to chemical engineering, in addition to materials science departments, are involved in materials research. Research in materials science is vibrant and consists of many avenues. The following list is in no way exhaustive, it just serves to highlight certain important research areas. Nanomaterials. Nanomaterials describe, in principle, materials of which a single unit is sized between 1 and 1000 nanometers but is usually 1 to 100 nanometers. Nanomaterials research takes a materials science-based approach to nanotechnology, leveraging advances in materials metrology and synthesis which have been developed in support of microfabrication research. Materials with structure at the nanoscale often have unique optical, electronic, or mechanical properties. The field of nanomaterials is loosely organized, like the traditional field of chemistry, into organic nanomaterials such as fullerenes, and inorganic nanomaterials based on other elements, such as silicon. Examples of nanomaterials include fullerenes, carbon nanotubes, nanocrystals, etc. Biomaterials. A biomaterial is any matter, surface, or construct that interacts with biological systems. As a science, biomaterials is about 50 years old. The study of biomaterials is called biomaterials science. It has experienced steady and strong growth over its history, with many companies investing large amounts of money into the development of new products. Biomaterials science encompasses elements of medicine, biology, chemistry, tissue engineering and materials science. Biomaterials can be derived either from nature or synthesized in the laboratory using a variety of chemical approaches utilizing metallic components, polymers, ceramics or composite materials. They are often used or adapted for a medical application, and thus comprises whole or part of a living structure or biomedical device which performs, augments, or replaces a natural function. Such functions may be benign, like being used for a heart valve, or may be bioactive with a more interactive functionality such as hydroxyapatite-coated hip implants. Biomaterials are also used every day in dental applications, surgery, and drug delivery. For example, a construct with impregnated pharmaceutical products can be placed into the body, which permits the prolonged release of a drug over an extended period of time. A biomaterial may also be an autograft, allograft or xenograft used as a transplant material. Electronic, optical and magnetic materials, semiconductors, metals, and ceramics are used today to form highly complex systems, such as integrated electronic circuits, optoelectronic devices, and magnetic and optical mass storage media. These materials form the basis of our modern computing world, and hence research into these materials is of vital importance. Semiconductors are a traditional example of these types of materials. They are materials that have properties that are intermediate between conductors and insulators. Their electrical conductivities are very sensitive to impurity concentrations, and this allows for the use of doping to achieve desirable electronic properties. Hence, semiconductors form the basis of the traditional computer. This field also includes new areas of research such as superconducting materials, spintronics, metamaterials, etc. The study of these materials involves knowledge of materials science and solid-state physics or condensed matter physics, computational materials science and materials theory. With the increase in computing power, simulating the behavior of materials has become possible. This enables materials scientists to discover properties of materials previously unknown, as well as to design new materials. Up until now, new materials were found by a time-consuming trial-and-error process, but now it is hoped that computational techniques could drastically reduce that time, and allow us to tailor materials' properties. This involves simulating materials at all length scales, using methods such as density functional theory, molecular dynamics, etc.